Hello and welcome to a new video. Now first of all, thanks a lot to Philip who let me use his camera while I don't have access to mine. Now I'm very excited about this particular video because this shows something that is usually not accessible to non-professional users of that kind of technology. Usually you need quite expensive equipment to be able to visualize this. So in this video we're going to look at frequency modulation and in particular how analog input to a transmitter is frequency modulated and then demodulated again at the receiver. This then goes into terms like frequency, deviation, modulation index and things like that. Now usually if you're familiar with my videos, you know that I will first discuss some theory and then show some experiments, but this time I'm going to flip it all over because I have to do the same experiment basically twice. So instead of doing that, we'll just look at the equipment first and then talk about theory later. So what I have here is my oscilloscope that I will use basically as function generator. That's the idea here. So I'm just using the function generator feature. I turn this on in a second, so you see that this is generating a sine wave here, and I hooked up the one probe to display the frequency wave, the waveform that I'm generating, but other than that I just use it as a function generator. So let's turn that off again. Now I'm feeding this via that cable here into the radio. This is a port here at the radio that essentially goes directly to the exciter, so there is no filtering going on whatsoever. This directly is modulated as is. There is no pre-emphasis or anything, so I'm doing that, and I've got a little wire here that I can use to essentially let this radio start transmitting. I'll demonstrate that real quick too. Now it's transmitting here at maybe 5 watts or so. I could make this neater, but I tried and I broke the connector, so anyway, that's what it is. The radio itself is just connected here to a dummy load. Let me show you that too. This is the dummy load here. Actually, it's not a dummy load, it's a power attenuator that I even terminated in 50 ohms, but that doesn't really matter. So anyway, so that's the transmitter side of things. And also I have this little guy here, that's an aluminum box, and inside this box there is one of these RTL dongles that I used in the previous videos. So even though this looks a bit different than what I had in the last video, that's basically what it is. It's just one of these dongles without anything special inside the box. I could put an antenna here on that BNC connector, but it turns out that this is generating so much stray RF here that I don't need that. So it's sufficient. This is enough for me to pick up what the radio is transmitting into the dummy load, and that's what I will then use to visualize. Now let me switch to the screencast because I'm using gnuradio to basically capture whatever I'm transmitting here with the radio, process it a little bit and display it in an interesting way. Okay, so that's the pipeline that I'm using to run my experiment. This is inside the gnuradio component, and if we look at the individual blocks, we have here a Osmocom source. That's the source for the signal that is sampled by the SDR hardware. This is tuned to 439.15 MHz. In Europe, that's inside the 70 centimeter amateur radio band, and that's also the frequency to which my radio is tuned that we saw before. Now, the signal that is sampled here by the SDR hardware goes straight into an FFT sink. So that will just display me whatever this hardware is capturing is displayed by this block here in the frequency domain. It's also fed into a low-pass filter and a resampler. Now, the reason for that is twofold. First of all, resampling this means that I have to deal with much less data, so this will run much smoother downstream. The data that gets into the resample is sampled at 1.5 megahertz here, and after resampling, I have 240 kilohertz. So you get that by multiplying by 4 and dividing by 25. So the information here is much less, and I can deal in a more efficient way with that here. So that's one of the reasons, and also downsampling here means that I will look at the FFT downstream here, and that FFT will be kind of zoomed in, and that allows me to have a closer look at what I'm interested at. So that are the two reasons for resampling here, and in order to be able to resample, I first have to filter, because as I said, this is resampling to 240 kilohertz, and due to the Nyquist theorem, any input frequency higher than half of that, that is 120 kilohertz, will alias back into my baseband, and I don't want to have that, so I have to filter out these. I'm filtering this in a way that the stuff that I'm interested in will be inside the passband. We'll see that in a second. Now, this resample data here is fed straight into a FMD modulator and then to an audio sync. So that part here just allows me to hear the signal. That's all. I will just be able to hear if I'm injecting something with the signal generator. I will hear that tone. That is not essential to the experiment, but it's a nice thing to do. Also, the resampled data is resampled once more and then fed into an FFT sync. So remember that we already had an FFT sync here. Now the difference between these two is this guy is displaying everything that is captured by the hardware. This is after resampling, so and after filtering also, so I will have a filtered and resampled view of that will zoom into the part that I want to see. And maybe the most tricky bit here is the center branch. First, I'm demodulating this. This is demodulating without any de-emphasis or anything, so it's like really taking the signal that is in there and feeding into a resampler and an FFT sync and a scope. So it's kind of confusing because there is sort of 3 FFT syncs here. This guy will show me the whole band that I'm sampling, or the part of the band that I'm sampling. This guy will be the same, but zoomed into the interesting part. And this guy is actually an FFT of the modulation. So it's an FFT of the signal that I'm injecting with the function generator. This is in baseband. So if I'm injecting, let's say, a 1 kilohertz tone, I should see a 1 kilohertz tone here. And that is the same, but as a scope sync that is represented in the time domain. If everything works out as planned, I will see a 1 kilohertz wave form here, a sine wave here in this scope sync. So let's turn it on and see what happens. Okay, so that is the whole pipeline running, and there is 4 displays here. The display at the top left is the band FFT, is an FFT of the whole of what the SDR is sampling, centered around 439.15 megahertz here. At the top right, there is the channel FFT. That's an FFT of the filtered and resampled data. And there is 3 interesting things to note here. First, there is this little peak at the center here, and no matter what frequency I tune into, I always get this peak. And most likely that is just LO feed through an artifact of the SDR hardware, of the way this hardware works. There is a little imperfection there that leads to this. There would be ways around this, but I'm not going to bother, so just ignore that little peak here. Then next, as opposed to here, where the noise floor is completely flat, we have a shaped noise floor here, because the filter is shaping the noise floor as well. Of course, it's filtering everything, so if I inject a signal that is out of band, it would be attenuated equally. But since this is not happening, I'm not transmitting anywhere, it's just a noise that is attenuated out of band. And lastly, if you look at the frequencies, that's a span of 1.5 megahertz here, and here we only have 120 kilohertz. So that is due to the resampling, and this will allow me to see sidebands here that I won't see here, just because the resolution is higher. At the bottom we have a baseband FFT, and a scope screen, a time domain representation of the baseband signal. Okay, so now let me start transmitting without any modulation, so I get just a carrier. Let me turn it off. Look at this, that's the carrier here. I turn it off, the carrier is gone, and if I turn on the transmitter again, I get this carrier here. Now interestingly, I don't have a carrier here, and the reason for that is even though my SDR hardware is tuned to 439.15 megahertz, the crystal clock reference inside the hardware is fairly poor. Actually, it is so poor that I have a frequency offset here that I don't see here. Well, maybe a little bit, because it should be, well, actually no, I don't think it can be seen, but here clearly it's just the carrier is not is outside of either outside of that screen or somewhere in the stop band where it's attenuated by the filter. But that is easily fixed by just clicking on the carrier here and clicking on it here again to really center it very well. And now the SDR hardware is not tuned to exactly 439.15 megahertz anymore, but this is just compensating for the error of that clock. So that's nice. And here I have a flat noise floor here because I don't have any modulation at all. So basically this should be full quieting my receiver here. And equally here, that looks like a mess, but it's just auto-scaling to a scale that is not really significant. So if I turn on the function generator now and feeding a 5 kilohertz sine wave into the system, I can see that sidebands appear here. Let me turn it off again, just the carrier, and if I turn it on, I've got 2 sidebands on either side. And these sidebands are spaced 5 kilohertz apart from each other. So if that's the center frequency at 0 kilohertz here, that is plus 5 kilohertz, minus 5 kilohertz, plus 10 and minus 10 kilohertz. And if I play with the amplitude of the signal of the modulation and reducing it, you can see that there's funny things going on with the sidebands. They sort of rise. The higher the amplitude, the more sidebands I have, but the spacing does not change. The spacing only changes with when I change the frequency of the modulation, which I'm going to do in a second. So that is kind of an important thing to note here, that we always have the same spacing regardless of the amplitude of the baseband signal, although the higher the amplitude of that signal, the more sidebands we get. And in the baseband here, well, clearly there is a peak at 5 kilohertz here. That's not surprising. And also, that should be a 5 kilohertz sine wave, but there is a bit of a sampling issue going here, so that doesn't look so nice. It will look a bit better when I reduce the frequency. In fact, that's exactly what I'm about to do. So I will set the amplitude back to a high level so that we really get nice sidebands here. Let's say 4 volts. Nice. And then I will knock down the frequency from 5 kilohertz to 1.245 kilohertz. And what should happen here is the sidebands should move closer together, and that peak here should go all the way down to 1.245 kilohertz as I do this change. So I'm now at 5 kilohertz, that's 4.5, 4 kilohertz, and already the sidebands are much closer together. They are now spaced 4 kilohertz apart and not 5 anymore. If I turn it down to 3 kilohertz, to 2 kilohertz, sorry, they're even closer. There's also funny stuff going on with the magnitude, and we'll discuss that in a second. And I've got this peak here at 2 kilohertz, and also that looks much nicer now. But I'm not caring too much about that. So anyway, the frequency that I wanted to set was 1.245 kilohertz. So I'm now at 1.2 kilohertz, and I'll knock it up just a little bit to get this 1.245 kilohertz. Great. So I see here lots of sidebands here close together, spaced 1.245 kilohertz. apart from each other, which is not surprising. I've got this peak at 1.245 kilohertz and a 1.245 signage waveform here. There is a bit of intermodulation product going on here, but let's ignore that for a second. So if I now play with the amplitude and turn it all the way down, it's now down at 20 millivolts peak to peak, which is as far as it goes, and I'm back to pretty much just a carrier, which makes sense because I'm hardly modulating that carrier anymore. And now I'm going to turn it up again. I'm now at roughly 100 millivolts peak to peak. I can already see two sidebands here rising from the noise. Now if I continue that procedure, let's say 500 millivolts peak to peak, roughly, there is more sidebands showing up, and this peak is growing as I increase the amplitude of the signal generated by the function generator. Now, if I turn it up and up and up, now I'm at roughly 2 volts peak to peak, and I got even more sidebands, and now something interesting is starting to happen. I'm now at 2.2 volts peak to peak, and somehow the carrier here itself is disappearing. Let's continue. 2.25 kilohertz, 2.3 kilohertz, and the carrier is really dropping and dropping and dropping further and further. I'm now at 2.41 kilohertz, 2.4342, and that's about as low as I can get this carrier here. I can still see the yellow feed through that I talked about at the very beginning, but at 2.42 volts peak to peak, somehow I managed to get rid of that carrier. I'm wondering whether that is a coincidence that that's just 2.42 volts peak to peak, because that's sort of an interesting number. But anyway, so there is that. So we have, for a frequency wave form, a sine wave of 1.245 kilohertz, at this particular amplitude we managed to get rid of the carrier, and the rest is just business as usual. I mean, I've got this peak here and also a signage waveform here. So let's grab some pen and paper and discuss whether we can use this for anything useful. So let's briefly revisit frequency modulation in order to understand why the things that we've just seen are not only interesting from an educational point of view, but can also be very useful in order to achieve various things. Now, all these pictures here are from Wikipedia, and I'm planning to first discuss the modulation scheme per se, and then introduce the terms deviation, modulation index, and then look at how this boils down to the sideband pattern that we saw in the experiment. In this top plot here, there is two graphs. One is a dashed line here, and I'm going to call this the baseband modulation. So the modulation is just the information that we're actually interested in transmitting. So that's actually the information, the modulation baseband signal. And then the solid line here is the modulated carrier. Now, if we have no modulation, a modulation of 0, this is oscillating at a particular carrier frequency. And I'm going to call this resting frequency, just to be clear on the terms here. And the resting frequency in the experiment was 439.15 megahertz. And that also happens to be the frequency of the carrier. It's just a frequency that you have when there is no modulation whatsoever. Now, if the modulation increases, gets positive, then the instantaneous frequency of the modulated carrier also increases. You can see that this is kind of at a higher frequency than here. And likewise, if the modulation gets negative, the instantaneous frequency of the modulated carrier gets below the resting frequency. So if we plot the deviation from the instantaneous frequency of the modulated carrier to the resting frequency, we get this. Again, when there is no modulation, we have a deviation that's called instantaneous deviation of 0. If we have a lot of positive modulation here, then we have a large deviation from the resting frequency, and we have the same thing here as the modulation gets negative. Now, obviously, the shape of that line here and that line here are the same, because that's the whole point of this modulation scheme. We increase the modulation, and by that we also increase the instantaneous frequency of the modulated carrier, which is nothing but increasing the deviation. So the deviation kind of follows the modulation, which sort of leads to the question how much we're deviating, because let's keep things simple and say we have a 1 kilohertz modulation here, a baseband signal of 1 kilohertz that we want to modulate, and we have a resting frequency of the carrier at, let's say, 10 kilohertz. Now, the instantaneous frequency here must be higher than 10 kilohertz, right? Because that's the resting frequency, and we just said that if we have positive modulation, then we increase the frequency. But by how much? It could be 12 kilohertz. Then we'd had a deviation of a peak deviation of 2 kilohertz here, because we have a 10 kilohertz resting frequency, and we increase the frequency by 2 kilohertz, so we end up with an instantaneous frequency here of 12, and in the lowest case here of 8 kilohertz. That's called a peak deviation of 2 kilohertz. But we could also have a peak deviation of 5 kilohertz or 25 or 75 or whatever. So we sort of have to agree on something here, otherwise everybody would set up his radios differently. And the thing that ties the deviation to the modulation frequency is called modulation index, and it's just the ratio between the deviation and the modulated frequency. So in the example that I just had, we have a frequency here of the modulation of the baseband signal of 1 kilohertz. And if we move 2 kilohertz up here in this case, and 2 kilohertz down, we have a peak deviation of 2 kilohertz, which would mean that we'd had a modulation index here of 2 kilohertz, the peak deviation, divided by 1 kilohertz. So that's essentially what the modulation index is. And we can also solve this equation, obviously, for the modulation frequency, which then boils down to deviation divided by modulation index. Now let's look how this ties into the sideband thing. Now, first of all, what happens if we increase the amplitude of the modulation? That's what I did in my experiment, right? So I'm going to increase this amplitude here. That will naturally also increase the deviation, because we just said that these two graphs here are kind of tied together. But increasing the deviation at the same modulation frequency means that we're increasing the modulation index. That's what this equation here says. So what I essentially did when I knocked up the amplitude of the modulation was increasing the deviation, and thereby increasing the modulation index. Now, there is a complicated mathematical relationship that explains where the sidebands are of an FM modulated signal, and how large they are, what their magnitude is. And I'm not going to kind of derive that or whatever, so I'll just show you the result. That's a bunch of Bessel functions of the first kind of various orders here. And it turns out that the carrier, the magnitude of the carrier that we saw in the plot during the experiment happens to correspond to that first line here. The magnitude of the first pair of sidebands correspond to that. The magnitude of the pair of second sidebands correspond to that, and so on. So basically there is a lot of information in here. First of all, if we have a low modulation index, and remember that this corresponds to a low amplitude of the modulation, then we have a large carrier and almost no sidebands, kind of weak sidebands, first pair of sidebands here, and kind of no further sidebands at all. Although you can see that they are kind of here mathematically, they're not zero, because because there may be 0.1 or whatever, but it's really a very low number, which is why you don't see them during the experiment. And as you increase the modulation index further, the carrier drops down and more sidebands appear, and there is a point where the carrier is 0. When the carrier becomes, when that graph becomes negative, it just means that the carrier starts to rise again with the inverted phase, but whatever. So we're interested in this 0 crossing here, and that 0 crossing happens to be at 2.41. So at a modulation index of 2.41, we happen to have that 0 crossing of the carrier, which we were able to measure during the experiment. So what exactly does that mean? It boils down to, let's say we want to generate an FM signal that has a deviation, a peak deviation of 3 kilohertz. Why would we want to do that? You saw in the experiment that the higher the deviation, because I increased the amplitude here, and we just repeatedly said that that corresponds to increasing the deviation. So the higher the deviation, the more sidebands you have. And you always have to kind of restrict the width of your signal, because if you keep going, then you get more and more and more sidebands, and at some point you start interfering with stations that are on nearby frequencies, and of course you don't want to do that. So this is why we have to agree on a particular deviation, which might be 3 kilohertz or 5 kilohertz or whatever, but that would be an application for this. Let's say you want to calibrate your radio to a peak deviation of 3 kilohertz. So by that equation here, you want a deviation of 3 kilohertz, and we know that the 0 crossing is going to happen at the modulation index of 2.41. So if we divide 3 kilohertz by 2.41, then we end up with a modulation frequency of 1.245 kilohertz, which is exactly the frequency that I set my signal generator to. So to summarize, what I did is I wanted to have a signal of deviation of 3 kilohertz. So I set a modulation frequency of 1.245 kilohertz, because I know that with these two values here, I'll get a modulation index of 2.41, and that means that I should have a 0 crossing there. And I can fiddle with the amplitude, that is with the deviation indirectly, until that happens, and then I know that I have fulfilled that need, and that I have a signal with peak deviation of 3 kilohertz. Okay, so in the next video I'm going to use exactly that to calibrate the deviation of my repeater, but I think it's a good idea to stop here and to make that a new video, because it's probably already quite long. I hope that was interesting. If you have comments or anything to share or discuss, please do so down in the comments, and thank you for watching.